Okay, introduce myself. I'm Roger Blanford. I'm a professor at the Department of Physics on campus and also at SLAC. And it's my great pleasure to welcome you to the 2025 Robert Hofstadter Memorial Lecture. This is a lecture series that goes back to 1993 and obviously memorializes Robert Hofstadter. I'm very pleased that Laura Hofstadter here with us in the front row, and many other people who knew Robert in the past. Just say a few words about Robert Hofstadter. He was a groundbreaking physicist, very much an instrumentalist, but not just a builder of instrumentation, somebody who had a very keen eye for the science that it could be done. It motivated what he did, and he then went forward and to use it in ways. And of the many things that he's associated with are use of sodium iodide in detectors, which is used to this day. He was a pioneer in particle physics. He used electrons, which is a completely innovative idea at that time, to probe the structure of nuclei, and taught us that the protons and the neutrons that are inside them are not point particles, and they have structure. And then there was a glorious story that went on beyond that. So he was a pioneer for that, and that work was recognized with the 1961 Nobel Prize, which he shared with Rudolf Nussbauer. More recently in his career, he saw that in astronomy, which is where I come from, was not just a business of your eyes, using visual spectrum, the whole electromagnetic spectrum, and in particular gamma rays. And he had the vision to firstly create a technology for one of the early gamma ray detectors, gamma ray telescopes, called the EGRET, which is our Cosmic Gamma Ray Observatory, and that was launched slightly after, just about a year after he passed away, but he was being gloriously successful, and then was succeeded by a Fermi Gamma Ray Space Telescope, which is led locally by Peter Michelson, who's here in the front row, and worked with Robert Hofstadter and has carried it forward. So Fermi Gamma Ray Telescope is the success of that, and it's making discoveries as we speak. It's been a wonderfully fertile part of physics and astronomy, and it's nice that it's named after Fermi, because Robert Hofstadter coined the usage of Fermi in memorializing Enrico Fermi as a unit of 10 to the minus 15 meters. So that's a sort of a nice thing. And the lecture that we're going to have in a distinguished line of Hofstadter lecturers is from Professor Stephen Cowley, who has had an illustrious career. He's currently director of the Princeton Plasma Physics Laboratory, which is a major responsibility, but he's also run major facilities, including Cullen Laboratory, the UK Atomic Energy Authority, where he was executive officer, and he's had a career that's gone backwards and forwards. He was educated originally at Oxford, but then spent time at UCLA and in Princeton and UCLA, then went back to England. Now he's back in Princeton, and all of his career has been, in some sense, grounded by the topic we're going to hear about today, which is the use of plasma physics to enable fusion reactions to power the planet. But he's also had a lot of interest way outside that line. Has continued his graduate work to his present responsibilities, and he's gone off way into astrophysics, gone off into other apparatus, and he's a sort of, like Robert Hofstadter, he's very much a broadly interested physicist who's interested in new opportunities and new discovery space. And so it's a great personal pleasure for me to welcome my colleague, Stephen Cowley, to come and give the 2025 Robert Hofstadter lecture, and it's going to be on, as you can see here, fusion energy, why, how, and when.
I'm not an economist, you ready? And every time you take off your jacket, it looks like the starting a fist fight. This is a great honor for me. Thank you so much for inviting me. And a huge honor to be here honoring the name of Robert Hofstadter. I'll get to the connection between my talk and Robert Hofstadter in a moment, somewhere in the middle of the talk, actually. So I'm going to talk about fusion and about where we stand in fusion at this moment. But I would like to start a public talk with one of the great public talks of all time in science. This is the talk that Sir Arthur Stanley Egerton gave in 1920 to the British Association for the Advancement of Science. The then annual meeting was in Cardiff in August of that year. And he took as his topic the internal constituents of science. And it's a bit of an intimidating public lecture because, in fact, I think probably a little bit hard for the audience generally, and it's always hard as a public lecture exactly where you place it because the audience isn't the general person on the street. Some people are interested in physics, and so exactly where you put it. But what's remarkable about this lecture is he actually introduces a whole new set of ideas about how stars work and what they do, and the whole stellar astronomy at that time. And it's all done without complicated equations, a few numbers. So numbers are always important, but it can be read. You can find it on the web. It was published sort of verbatim in Nature, and so you can read the words and also the way he talked at that time, which was this sort of rather charming, semi-Victorian English. I always kind of wonder how it actually sounded at the time. But one of the questions that came up was, where does the energy radiated by stars come from? Because, and he makes this point in the lecture, for about 60 years, we've been living actually with something that most people thought was, if they really asked themselves the question, was wrong. The theory as to why the sun was hot and why it was giving out photons and radiating was dated back to Helmholtz and Kelvin in the 1860s. And it was the theory of what he called contraction, which is you have a great big ball of gas, and that big ball of gas has gravity and it's pulling on itself, and it pulls itself inwards. It loses some potential energy, that gets converted into heat, that gets converted into pressure, it holds up the ball of gas, it has pressure, holds up its gravity. But then it radiates some more, it gets cooled, and the pressure diminishes a little bit, so it shrinks a little bit further. And it radiates a bit more, and it shrinks a little bit further, etc. And this contraction theory of why the sun was hot was prevalent right up until this talk by Eddington in 1940. And yet there was lots of evidence that it wasn't true. Right? Famously, of course, Charles Darwin had estimated the age of the wheel in Kent to be, I think, 300 million years old. And Kelvin had estimated the age of the sun due to this contraction process to be 20 million years. And so there was a distinct contradiction between all kinds of evidence, this astronomical evidence that Eddington points out in his lecture, geological evidence of Darwin's argument was about the erosion of the rock in the wheel and how long it would take to get that amount of erosion, etc. But there's lots and lots of different pieces of evidence why this was wrong. But it had held out, partly because Kelvin was kind of an influential guy, and there wasn't another theory around. But the other part of this lecture that's fun is that he was also lucky. Because only a few months before, Aston, Cambridge, had measured the masses of hydrogen and helium to enough precision to recognize that it wasn't quite 4 hydrogens that made up one helium. So then he had measured the mass of hydrogen, which in atomic units, helium is defined to be 4 atomic units of mass. Hydrogen has this 0.8% difference from 1. And so if you could put 4 hydrogens together, put 4 hydrogens together to make one helium, you would have some missing mass. Now, of course, hydrogen, this is a proton, this is a proton, right? And it's got an electron going around it. And he said, well, in order to make the helium, you've got to capture those 2 electrons into the nucleus and form the helium. And he didn't actually know how that happens, and that's not exactly how it happens anyway. But he didn't need to know those things. All he needed to know was the mass before and the mass afterwards. Calculate how much energy you got from turning 4 hydrogens into helium. Didn't know the existence of a neutron at that time. Right? Didn't understand what it was, so the other 2 particles in the nucleus at the time. But he didn't need to know it. So if you actually take that, right, and you say, okay, we imagine that the sun has some 1/3 hydrogen, and it's converting all of that into helium. How long would the sun actually shine? He came up with 15 billion years. That's actually quite a good estimate of the lifetime of the sun at that time. And what's really nice about this argument is that it doesn't really take knowing very much. You don't have to know how to solve differential equations or anything else like that to actually get this argument and to figure out. So what he said at that time, and there he is, and this is a quote that almost everybody in fusion always knows by heart, right? This reservoir can scarcely be other than the subatomic energy which it is known exists abundantly in all matter. We sometimes dream that man, these were somewhat sexist times, will one day learn how to release it and use it for his service. The store is well nigh inexhaustible, if only it could be tapped. So I like to start with this, partly because usually at the end of every public lecture that I've given on fusion, somebody tells the fusion joke, which is it's 30 years away or it's will be. And I said, no, it's been 100 years. So it just happened. So why do we need fusion at this time? This is a good question. We see the cost of renewable energy coming down dramatically, and this is really a good thing at this time that we really want to tackle climate change. At least I want to tackle climate change. I suspect some of the people who want to tackle climate change. It's good to see that. So why would we worry about developing another power source at this time? And you can look at this in many different ways, and this is not definitive. We have a group at Princeton doing something called Net Zero America Project, looking at what we would need to do to decarbonize our energy systems, and what we would need to do, in particular in this case, to decarbonize. This is the northern system of basically New England, right? An analysis of that system and bringing in different energy forms. And what you're looking at along the bottom here is CO2 emission limit. So imagine we put in an emission limit and say we want to reduce from 200 grams per kilowatt hour of electricity down to 0, right? What would be the average cost of electricity? Now, these kind of analyses, I hope I won't insult too many people in the audience, are a bit like very complicated guesses about what you could do in the future, etc. But it gives you some idea to put your policy on at that time. And this one was done by the group at Princeton and MIT to look at this. And what does these actually mean? So they looked at having a mixture of 3 different kinds of electricity generating. Fuel saving would be something like solar, wind, hydropower, etc. And you do a fair bit of that, right? And on the left, they have fast bursts. So this would be energy storage and flexible demand, etc., in order to get rid of the small fluctuations over days and hours. Right? This is kind of good storage, batteries, etc., on that kind of scale. And you'll see on the left here that as we reduce the CO2 emission limit, having trouble with my pointer, as we reduce the CO2 emission limit, the average cost of electricity rises dramatically. This is unacceptably expensive. If electricity costs that in the United States, then bringing back manufacturing or whatever you want to do in that instance would be impossible. Our energy costs would be too large for that. But now if you add to that something like nuclear, gas with carbon capture and sequestration, bioenergy, synfuels, I'm using what they say in their reports, right? What you see is as you reduce the carbon, and of course there's a spread here because they're looking at different uncertainties, right? There's a much more acceptable rise in the cost of electricity over that period. Now, when we first started, and this paper here looks at fusion being that firm low carbon energy source that you add to the fuel mix in the northern system. So around about the January of 2022, I got a call from the White House because there'd been a lot of activity, political activity, with fusion startup companies coming forward and pushing fusion and saying we've got to accelerate fusion. And so we got a call at Princeton, and a set of people came up from the White House and the Department of Energy to talk to us about what it would take to accelerate fusion. And the argument was frankly, we don't think we can get large-scale deployment of nuclear, of conventional nuclear, and therefore we've got to be looking for another firm energy source to fit into that slot right there. This was the argument. Now, I'm not going to endorse the argument or anything, but this is the argument why, at that point, the White House got very interested in accelerating fusion. I think it was partly the attention of the private companies, it was partly the need to find other firm energy sources, etc., and partly results that were starting to show some progress in fusion science at that time. We then had a meeting at the White House, what we called it, the Fusion Summit, in March of that year, and this statement came out of that initiative at that time, that we should launch an agency-wide initiative coordinating across program offices to develop a decadal strategy to accelerate the viability of commercial fusion energy in a partnership with the private sector. The 2021 National Academies of Science, Engineering and Medicine report, Bringing Fusion to the US Grid, serves as a guiding document for the new initiative. This is that report. And it came out in 2021. And it said the Department of Energy and the private sector should produce net electricity in the fusion plant in the United States in the 2035 to 2040 timeframe. This is a stretch goal. There's no question that getting electricity in the 2035 to 2040 timeframe would be actually going quite fast at this stage in the development of fusion. We have yet to get to a sustained fusion burn at this point, so imagining that we're producing electricity in that time is a stretch. We've taken it as our goal, and I think it is a reasonable stretch goal. However, it is nothing like the kind of goals. Sorry, I'll get to that in a moment. And we see that the incoming, well, I suppose it's come in, Secretary of Energy Chris Wright, is interested in fusion, and the current administration is also interested in fusion, and said we are working to launch the long-awaited American nuclear renaissance fission and fusion. And I personally also think that one of the things we should be looking at this time is another generation of fission in the United States to provide that firm part of the energy. And the incoming, he's the nominee for the Undersecretary of Energy for Science, Dario Gil, who is currently the vice president at IBM for science at IBM, and I think I'm looking forward to him taking up his post in DOE. It is time to build a quantum-centric supercomputer. It's time to elevate the capability of AI to advance scientific discovery and solve problems in ways we never could before. It's time now in fusion to shave off decades of developments and time cycles. This is a real challenge to the fusion. We should take it. We should take that challenge and we should see what we can do to work with that challenge and see if we can get to that 2035 time scale. Simultaneously, the investment in fusion startups has been astonishing. We've seen about 8 billion invested in fusion startups in the last 6 years. These startups vary from some really quite credible ones, doing some really interesting science, the ones that I described in front of Senator Manchin's committee as bonkers. Is that a technical term? And I say yes. But I mean, this is energizing to the community. What you can see here is the years basically starting here at 2013 going forward. There was an enormous, the blue line is the investment that year, enormous investment in 2021. As I say, some of these companies are doing interesting things. They're all highly dependent on the national labs and the universities to supply them with technology, with science, etc., in order for them to make progress. They cannot do it on their own. There's no question about it at this stage. So this is energizing our field very much at this time. Some of these startups, I mean, you'll heard of some startups that are promising commercial fusion by 2028. I think part of the problem here is the timescale for venture capital and the timescale to develop fusion don't actually line up. Right? We have an awful lot to do in this intervening time, and these two timescales don't line at this time. And that is probably problematic for us, because if expectations are so high, right, we can only disappoint. Right? And it's difficult to be successful if you're always disappointed. So it's a challenge, I think, to the national lab system. It's a challenge to universities to speak the truth in this time. Fusion will come sometime, and we will have solved the problem sometime. But if we try, if we imagine it's going to happen tomorrow, we'll be solving the wrong set of problems at this time. What's steel count? Oh, that's the number of it. So that's the number of different companies that have been set up. Right? You can see the white numbers.
That's how many companies.
That's how many companies were set up that year. Yes. Some of them were very flexible, as I said. Maybe I shouldn't use the word bonkers, but it just sounds like. Well, how? Let's go back a little bit. And this is, I'm going to try and I'm incorrigibly a physics professor and would like to talk about some physics. So let's get back to some of that. You know, one of the really frustrating things of all the fusion reactions that you could possibly imagine doing, the easiest one to do is between deuterium, heavy hydrogen, which is, here we are, here's deuterium. That's one proton, protons are green in my picture, and one neutron. And tritium, which is super heavy hydrogen, which is one proton and two neutrons. And this reaction is by far, it has cross sections about 100 times the nearest cross section to it, the easiest fusion reaction to do. It's easy for two reasons, one of which is that it's to do fusion, you've got to get two charged particles together. So you've got to overcome their Coulomb repulsion so that they get close enough that the strong force that binds the nucleus together can act and pull them together and do the fusion itself. Right? And so if you want an easy fusion reaction, you want the least charged particles. So you want hydrogen. Right? So we have heavy hydrogen and super heavy hydrogen. But the other reason this is a very, very good large cross section is it's a resonant cross section. When you get deuterium and tritium together, and you put them together into helium-5, there's an excited state, helium-5, a J3 state of helium-5 at 104 kilowatts. And quantum tunnels into that state, and that dominates the cross-section. And that's why this is by far the easiest fusion reaction to do. Now, it's really God's little joke. It's God's little joke, really, because tritium doesn't exist in them. It's a radioactive isotope that decays to helium-3 in about 12.5 years, right? And you have to make it in order to put it into the fusion reaction. So this is really not all of the nuclear physics that you have to do, because I should go back a little bit. Deuterium and tritium. You round them together, they get over their repulsion, they form helium-5 for a moment, so then it splits up into helium-4, which is normal helium, plus a neutron. And the energy is carried away of the kinetic energy of the helium, 1/5 of the energy, and 4/5 as the neutron. And this neutron is a tank shell of a neutron, very, very energetic neutron, some 10 times the typical fission neutron energy coming out. Then you have to use that neutron to make some tritium. And you make tritium by bombarding lithium. And when you bombard lithium, 6 in this case, which is 7.5% of all lithium, it splits up into helium and tritium, and you take that tritium and put it back in your end. But because you in this case, the deuterium and tritium have to get over their repulsion, you have to heat them to a temperature when they're running around and they bump into each other, they bump into each other with enough energy to get over that repulsion and do the fusion. And that corresponds to a temperature of around, we would say, between about 100 and 200 million degrees. In the experiments we did in Princeton in 1994, when we first did 10 million watts of fusion energy, the temperature in the plasma, the hot deuterium and tritium, was about 250 million degrees. So you get into that temperature, the deuterium and tritium are running around, they bump into each other, and every now and again they make a fusion reaction. That fusion reaction releases gobs of energy, but in the form of an energetic helium nucleus, an alpha particle, and a neutron. The neutron comes out of your device, and you breathe your tritium in what's called the blanket here. And the blanket would be at some 600 degrees centigrade, typically in a fusion reactor, which is where you're going to extract your heat. The plasma. So whenever you get something to that kind of temperature, the electrons of the ion have been split off, and they're floating around in space. And the ions are floating around in space. So it's in the form of what we call plasma, an ionized gas. And the plasma can be self-heated in the fusion process because the helium comes out of the reaction and it bumps into some other piece of tritium or deuterium, gives up its energy and heats the gas and heats the plasma up to the temperature. So you can actually get it to burn, which is what happens in the middle of the sun. The heat that's produced by the fusion makes the fuel hot, and the fuel being hot makes fusion, and it keeps on burning like that. That is the basic process. It is kind of annoying that the easiest fusion reaction to do involves a substance that we don't actually have easily obtainable on Earth, and we have to breed it in a fusion reactor, and it's a radioactive gas. It would be so nice if it happened to be, another one of the hydrogen fusion reactions, but it ain't, right? There is enough. I always quote this, but obviously, if you start making fusion reactors with this reaction, your fuels are going to be deuterium, which you extract from seawater, and lithium. At the moment, that lithium you will probably just get from faulty brines in the Andes, which is where we get lithium for batteries at this point, right? But in the future, because you use so little lithium in a fusion reactor, you probably could extract the lithium from seawater. There's 0.2 milligrams a liter of seawater, and you could extract your lithium from seawater, and there's about 30 million years worth of lithium to power the planet's energy needs in seawater. So that's the promise. I mean, that's kind of why we all want to do fusion. Is you have millions and millions of years of steady energy production over that time. In principle, this is what you do. you have your plasma here in some kind of vessel being heated up, and in this case, held by magnetic field in that vessel. Right? Being heated up to this immense temperature, being heated up to that immense temperature. Right? It makes fusion, and in the walls of that device, in this blue part here, right? Sorry, just inside the blue part there, you have lithium where you breathe your tritium, and it gets hot because that neutron comes into the wall, it breathes tritium, it carries energy with it, it gets hot in the wall. You then boil water. You boil water and you power the steam engine. So it's a very complicated steam engine, but in the end, it's a steam engine. But you also have to extract the tritium from that blanket around the edge, right? Reprocess it and get it back into your image. And fundamentally, that's what we're trying to do. Now, we've been struggling for some years to get the conditions inside the plasma to do the fusion reaction. We've almost done none of the engineering of what actually would go on outside that in your device. For people who do laser fusion, it's kind of simple. You have a pellet in the middle of this device that you, with deuterium and tritium in it, you shine a laser on it, it does fusion. Around this thing, you have a lithium blanket where you breathe your tritium, right? It gets hot, you boil some water, and you make some electricity. That's fundamentally what we're trying to do. So I'm going to show a few equations because I kind of imagine, I know there's certainly some fantastic physicists in the audience, so that's a good proportion. You can handle at least some simple equations, and I'm going to do some cartoons to explain why it is that it's taken so long to get where we are. Okay? We've been talking about fusion really since the Second World War, and how great it would be to do fusion since the Second World War. So there must be reasons, some good solid physics reasons why it's been so hard, and I'm going to try and explain them. But to do that, first of all, here's the, if you take that deuterium-tritium reaction, the power density for the fusion reactions can be represented by a very simple formula. This is the pressure of the plasma in atmosphere squared. And typically in the middle of our machines, we want the magnetic machines, we get a few atmospheres of pressure, maybe 5, 6, 7, something like that. And so you get, if you get 7, say this would be a bit over 4 megawatts per square meter, per cubic meter in the middle of your device. And the peak of this reactivity happens at about 100 or 150 milligauss, something like that. That's your fusion. And 1/5 of that energy that's coming out of the fusion reaction, right, comes out in the self-heating, the helium that comes out, 1/5 of that energy. So if you're producing about as much fusion power as your heating power, that ratio of fusion power to how much you're heating your system, that's called Q in the business. You'd like Q to be really large because you wouldn't want to have to be pouring in heat to get energy out. You want it to heat itself. You want to light the fire and make it burn. These are a collection of results on the right-hand side from all of the world's magnetic fusion experiments. These are fusion experiments where the plasma is held in a magnetic field. I'll get to that in a moment, right? And these were the results. This green line here was Princeton in 1994. We got to 10 million watts for about a second. Then on the Joint European Torus, where the lab I used to run in the UK, we got to 16 million watts in 1997. And then just December of 2023, they sustained about 12 million watts for about 5 seconds in that device. That's significant amounts of fusion power. It shows you can get the conditions for fusion. You can get that shot was again at about 200 million degrees, and you can actually make fusion happen. And very recently, I'm not going to talk about laser fusion because there are other people who are much better qualified to do it, but spectacular results at the National Ignition Facility. The latest result was just over 2 megajoules of laser energy went in, and 8.6 megajoules of fusion power, of fusion energy came out of it, which is a cubical sport. This was after basically 15 years of hard scientific work. When they started that experiment, it was incredibly disappointing. And after 15 years, they've got to this amazing state at this time. I want to say, because I always say this in front of the politicians, that's why we have national ones, right? Because they can figure out problems like this and make things work. So we're getting some with you. So the configuration that we work on at Princeton dates back, and it's varied, dates back to the 1950s, and Andrei Sakharov, the Russian physicist turned dissident. And fundamentally, what we have to do, we have to isolate the very hot stuff that's doing the fusion from the walls, so it doesn't get cold, right? And the walls don't get up to 200 million degrees, because then they would melt. So what we do is we put the plasma in a bottle. And that bottle is basically, we take a solenoid and we bend it around. So these coils here, solenoid coils, and they're bent around, and they make a donut-shaped magnetic field that goes around itself like that. And we have a vacuum vessel that holds the air from coming in, and the purple stuff is the plasma here. And then what we do, we turn on the coils, we puff in deuterium and tritium. Then what we do is we change the magnetic field through the hole in the middle, right here. This solenoid coil here, down the middle, changes the magnetic field through the middle. By Faraday's law, that induces a voltage around this one. And what happens at that point is that the plasma breaks down, the electrons go one way, the ions go the other way in the voltage, and we get a current that flows around the loop. Typically, in today's device, millions of amps of current go around the loop. Now, what happens when you have light currents? You have two wires going like this, with carrying currents in the same direction, they attract each other. Those two wires, light currents attract. It's high school physics, right? And what happens to this tube of current going around is that the top half attracts the bottom half, the left attracts the right. It attracts itself and pulls itself off the wall. That's called the pinch effect. At which point, you've got your plasma in the middle, not touching the wall, right? And you can heat it up to these immense temperatures. And the figure of merit of this magnetic bottle is called beta. It's the pressure of the plasma, P, here, divided by the pressure of the magnetic field, because the magnetic field acts like it has a pressure on it, and that's in I handed down the units. The pressure of the magnetic field in atmospheres is 4 times the magnetic field squared in Tesla for physicists in the audience. Right? We can typically get this number, beta, to 5 to 10% in our devices. So we don't utilize the pressure of the magnetic field terribly well, but we can get it to those kind of temperatures, those kind of pressures. The fusion power, remember, went like the pressure squared. So then if you take this formula and replace the pressure by beta times B squared, you get actually the fusion power density is proportional to the 4th power of the magnetic field. It's a very steep function of the magnetic field inside the units. Right? And therefore you have companies like Commonwealth Fusion at MIT who are trying to double the magnetic field that we can attain in our devices, because you get 16 times the power density inside your device. Right? And using high temperature superconductors to do. That may or may not be a successful strategy, but it's certainly worth trying something. Now, one more thing, so we understand the parameters here. There's just one more parameter of your device that's very, very important. And this is the one we're not doing terribly well. Right? So if you imagine what's actually happening inside these devices, and we didn't know this till probably the beginning of the 1980s, is that the middle of this plasma is at 200 million degrees, but the edge is at 10,000 degrees. And there's a huge temperature gradient across there. And it's pretty much like, if you take the saucepan and you put it on the hob and you turn on the gas, the heat on the bottom, you start having turbulence. Right? The hot stuff rises, the cold stuff falls, you start to get turbulence inside your device. And in our devices, they're really quite turbulent. Actually, it's bubbling away, and that turbulence is carrying hot stuff outwards and cold stuff inwards. Right? And this means that we're leaking heat. we were trying to make a thermostat out of a magnetic field to lock up the heat inside this device. But actually, this turbulence is bringing hot stuff out, it's bringing cold stuff in at that time. Right? And we measure that by something called the energy confinement. And in the best device, the energy confinement time might be about a second. Right? We're hoping in the international Tokamak it's about 4 seconds. And so what happens is, if we want to get the plasma to be heated by the fusion reaction, we have to have the power density of the fusion in the alpha particles, the helium, right, has to balance the loss of energy from the plasma. Right? And this is the energy density of the plasma divided by this confinement time. That's the definition of what confinement time is. And what we want is that confinement time to be really long. We want it to hold the heat for a long time, so I don't have to have gobs and gobs of fusion energy to keep it hot. And so this condition for it to be self-heated is known since the 1950s. It's called the Hofstadter, and in these units of atmosphere seconds, it's given there. This is what we've been trying to do. This is the International Tokamak experiment back now, the ITER project, the biggest experiment in the world. 7 countries trying to do it. It's a very, very big machine. And the reason it's big is if you make the distance from the middle to the outside long enough, it's going to take a long time for the heat to go from the middle to the outside. Right? So you make it big enough, it's going to work, you want, right? And so this is being built in southern France. So if you want to build an experiment, put it in a nice place, and then the physicists will be happy. So it's next number of lots, so that's very nice. And this is what it looks like inside it right now. There's a segment inside. They had some problems. They had to take the segments out. They put them back in. It's being constructed at this time. It's making progress. And this just is exactly what you want to do, right? So let me explain this. This is a simulation of what we expect that to do, given the results from current experiments and benchmarking against the theory, right? This was a calculation done by Bob Buddy from Princeton. So at time t equals 0, you have this great big toroidal donut-shaped hole. You fill it with deuterium and tritium. Only a few grams of deuterium and tritium. Then what you do is you turn on your magnetic field. So you've got the magnetic field inside this device. And you induce, in this case, 15 million amps to flow around the loop. And then at this time here, you turn on heater beams. These are beams of neutralized particles that slam into the plasma and heat it up. So you've now gone from a temperature of typically about 10,000 degrees, 10 million degrees at this time. When you turn on the heater beams, it shoots up to about 100 million degrees in a second or two. Right? At that time, you start to see fusion. And on this side, we're plotting the fusion power. And this is the power that was self-heating the alpha particles. And at that time, so we've now turned on 70 megawatts of beam. Right? At this time, we step it down to 50 megawatts of beam. And at this time, we turn the beam on. So what happens, let's take scan 2. Now these different scans have different assumptions about boundary conditions because this is an experiment and we're not quite sure what's going to happen. Scan 2 goes up to about, you see here an instability in the middle of the plasma going backwards and forwards, and then it settles down to just over 500 megawatts of fusion power and nothing coming in. That's ignition. If ITER actually does this, I hope I'm still alive when it does it. That'd be fantastic, right? It's just a self-sustaining fusion power coming out 500 megawatts of power at that time. It'd be really spectacular. But this is sort of get to my thesis for this talk. We've gone along this line of making these devices. TFDR, which is a machine at Princeton that did 10 million units in 1994, to ITER, right, which we're building at the moment. The Europeans have then designed a power plant based on that concept. It's called the European demo. I just reviewed it actually. It's enormous. It's even bigger than ITER. ITER's going to cost us roughly $25 billion. this machine would probably cost about $50 million, right, to build at that time. I have great reservations. Right? We're on the right route to get a commercial power plant. I think we can get fusion out of this, but I don't think we can get a commercial power plant out of this. Right? It's technically challenged. Even that big design, and you made it big enough that it's really going to be self-heated and it's going to sustain the fusion burn. But at that kind of money, right, is a utility going to come along and order 10 of them? I don't think so. Right? We need some innovation between now and then, right, to make it smaller, cheaper, faster, and something that the market will really want to get. These results from the machines were good. We got to fusion. But these were large, expensive machines, and the ones that are actually going to get to a fusion burn are even larger and more expensive at that time. So this was basically, I think, Princeton has been in this state since about 2000, that most of the scientists at Princeton are on the move that we know how to do fusion, but do we know how to do commercial fusion? Because we're not in this just to do science. We want to actually make power out of fusion. And so fundamentally, we're not getting good enough confinement. That turbulence that takes the hot stuff out and the cold stuff in is too variable. And it's meaning that the confinement time is too short. And then we have to make the machine bigger so that we get a longer confinement time. And when we do, it gets more expensive. It's another problem. Surface area to volume ratio gets bad. We can't handle the heat fluxes from the edge. Everything starts to be much harder to do. If we could get a machine with lower turbulence, we could make a much better fusion device. Now, sometimes we get states of low turbulence inside the plasma. Sometimes we see regions of the plasma with a low turbulence. But we don't see it over the whole plasma, and it's not consistent at this time. So, this is where I get to the cartoon physics. This fellow over here, was known the dean of plasma physics, Marshall Roosevelt. Marshall Roosevelt came to Stanford in 1949 as a postdoc, and he published something called the Roosevelt Formula. And in the 1961 Nobel Prize lecture by Hofstadter, he compares the scattering vector to the Roosevelt formula that was derived here in Stanford in 1941. And so there's a little bit of a tribute in the published version of the Nobel Prize lecture from Hofstadter that is a tribute to the work that was done as a postdoc here. At that point, Marshall moved up to Los Alamos to work on the bomb at that time, but he became the leading theorist in fusion and was known as the dean of plasma physics. So I'm going to try and explain to you what this instability that's causing us so much problem is. And that will pretty much use up the rest of my time. Okay. So you've got these magnetic field lines that are lying on the toroidal donut-shaped surface. And sorry about my drawing, it isn't the best in the world. Somebody should clean it up, but it's not me. So imagine you've got these field lines. And then on those field lines, this is the motion of what we call a passing line. It's following those magnetic field lines and around the machine that you can't really see, but that's actually a little spiral. So the spiral looks sort of like that. So it's not very bright, is it? There's the spiral around the magnetic field line. That's a very tight spiral around the magnetic field line. So a typical deuterium ion would be doing that, going around the device. And this is that's a picture of that spiral. We tend to describe that spiral by the line going down the middle, which is called the guiding center, and then that ring that goes around the outside of the spiral at that time. That's the motion of the charged particle in the field. But there's also another kind of particle that exists on those surfaces, musical trap particles. They're still spiraling about the magnetic field, and they bounce backwards and forwards on the surface and process around the machine. These are natural calculations. This is not this is not cartoon. Not a very difficult calculation, but as it goes around the machine. Right, and those are called the trap particles. And you'll typically have 20% of your particles to be trap particles in the device. So inside that surface is another surface and another surface and another surface. It's really hot in the middle, the yellow bit, and it gets colder towards the outside. So you've got this big temperature gradient that goes into the middle of the plasma. And let's start the instability. You have to start the instability somewhere with some random fluctuation, and I'll start it with not a random fluctuation. But by painting the surface with, I'll have some cold trap particles here, some hot trap particles here, cold here, hot here, cold here. They're all lined up in the surface. And then I'll let them go. Now what happens if so the red particles are hot one, and the blue particles are cold one, is the red particle catches up with the blue particle. Because they process faster, the hotter particles than the colder particles. So now what happens is the cold particles are processing slower than the hotter particles. So right here, the hotter particles here are catching up with these colder particles. And you're getting an accumulation, a compression of the plasma right here, of the ions on the surface. And they're positively charged ions. And right here, between these two, the colder particles are the hotter particles are getting away, you get a depression in the density of the surface. So then what happens is that you get, right here on the surface, get an accumulation of, where's my pointer? You get accumulation of positive charge here, get accumulation of negative charge here on the surface from those processing particles. What that does, of course, is it makes an electric field. An electric field points from the positive charge to the negative charge at this point on the surface. So we started with stripes of hot, cold, hot, cold, hot, cold. The hot goes up with the cold and made positive charge right there. And between them, on the other side, negative charge. Right? And this produces an electric field on the surface of this pattern. Right? Now, when you have an electric field and you've got the particles moving in the magnetic field and the electric field, that motion of particles is not just the spiral around the field line, it also gets another drift. We call it the E cross B drift. And so if we have an electric field, in this case, pointing upwards, here's my electric field, right? Magnetic field pointing towards us, right? We get a drift of the particles in the direction of what we call the E cross B, which you get from your right hand. B field on the second finger, E field on the first finger, it's a drift to the right. So instead of just spiraling, it's spiraling and moving to the side. Now what happens if that happens here? So we've got this electric field, right? And, sorry, so I've got electric field, and we take the electric field right here, right? The electric field, I put my first finger on the electric field, I put my second finger on the magnetic field going up like that, and the motion is outwards. So what that does is it brings hot particles from inside the surface upwards to the surface and heats the surface. Just where it was hot, I make it hotter. And just where it was cold, I make it colder. Sorry, let's do that again. So this patch here was where it was hot, and it's got hotter. This patch was where it was cold, and it's got colder, and this patch will get hotter, etc. So what happened is we've amplified the original perturbation on the surface, and it's got hotter and colder in the stripes more. Another way to see it is here we are looking across the surfaces, and that E cross B motion, that flow, right, is in some parts pulling the temperature outwards, in some parts pushing it inwards. This instability is virulent inside the plasma. It causes the loss of heat from the plasma at a rate that is about 100 to 1,000 times the rate you'd have with no turbulence. And if we didn't have these rates, all the machines that we built in the 1970s and 80s would have actually done fusion at that time. This instability, it's called the temperature rate instability, is not just described in terms of cartoons. What we do now is we simulate these instabilities in codes that follow the charge ring of the particle. We have to, the particle going around the field line goes around very fast in comparison to these turbulent time scales. So you, instead of actually following the particle, you replace it by its average, which is the ring. This is called gyrokinetics. And we solve the motion of the particles and the magnetic and electric fields, and we get these simulations, gyrokinetic simulations, as we call them. This is one of, actually an early one, it's around 2010, 2011 or something like that. So this is one of the very crude early versions of this. During my lifetime, we went from looking at the disturbance inside the device and not being able to calculate anything about it and just having empirical formula for fitting, to this point at which we can actually calculate the disturbance. So, now, one more bit of physics and we'll finish up. So how does that actually produce the energy confinement time? So each one of these little eddies is about the size of one of those spiraling particle radius of that little spiral. It's called the Lambda radius of the items. And so if you want to get from the middle of the device here to the edge due to turbulent motions, imagine that turbulent motion is like a random walk. You take a random step forward, a random step backwards, taking a random walk. The distance you go in your random walk is the square root of the number of steps times the size of the steps, and this is the iron Lambda radius. And so the number of steps that the turbulence does to the plasma to get it from the middle to the outside, in the case of ITER, is about 1 million steps. These are tiny little steps each time turbulence does it. It takes from the middle to the outside. And the time it takes for one of these little swirls to turn over, is called the eddy turnover time, is basically the size of the device divided by the time it takes the time to go around the device, right? If you put this together and say the energy confinement is the number of steps times the time it takes to make one step, right? You actually get a formula that looks like this: that the energy confinement time scales like the square of the magnetic field, the size of the device cubed, and then the temperature of the -3 Hofstadter. We have an exact calculation of this now with our computer calculation, but it scales like this, right? And if you actually take the database of machines in the world, the scaling is all, and you fit it with a straight line, basically, you get almost exactly this formula. It's called gyrobone, this formula here. And this is the empirical fit to all the data from all the big Tokamaks in the world, all the big fusion devices in the world. And it's got this thing here. It's a fudge factor, we call it the age factor. And it can vary from about 0.7 to 2. But unfortunately, it's defined in such a way it appears in the formula to the 3.2 power. Which means that the difference between 0.7 and 2 is phenomenal in terms of confinement time. And we've got to do that, right? We've got to be on the higher end of this game. The truth is, we do see sometimes when this happens. Right? We do see suppressed turbulence inside the device, but we don't see it consistently, and we don't see it everywhere. So this gets to be to the weapon. We're just finishing building. Should be actually commissioning in December. A spherical Tokamak, a new compact Tokamak device, which we think has an X factor of about 1.8, which when you Google it is a pretty good H factor, right? And we're thinking of the first sort of teams of people coming to work on this device in 2026. And we'll begin the campaign at that time. Now there are 4 proposals to build a spherical Tokamak pilot plant in fusion sometime in the late 2030s, right? One of them is the British government's proposal called the STEP program in the UK, FAST, which is a company in Japan, and Tokamak Energy, which is a company that DOE is partly supporting is in the UK, and a design that we're producing at Princeton. If the results from this machine say that we get suppressed turbulence, right, then these things will go forward. If not, no. We won't have found a reduced turbulence device at that time. If they build that pilot plant, maybe we'll have commercial reactors in the 2040s. But this is ambitious. This is really an ambitious timeline at that time. The fusion companies believe we'll have a fusion reactor around about here. I really think a commercial fusion reactor around about here is a stretch, but we're going to try. I want to make one more point and then I'll stop. We've made huge progress in that business. In my lifetime, and particularly in the last 5 years, the codes have got so good that we can look at experimental data, we can look at the spectrum of the turbulence, and we can predict actually what happens inside the device. This is a step change because up to now, basically, we've been guessing our way to fusion. Right? We've been kind of using physical intuition and saying, well, we've lost something like this, see how it works. Right? Now we have the computational capability to try and predict what happens. But it's a massive multi-scale problem. Right? We start with the timescales for an electron to go around the field line, which is 10 to the minus 12 seconds. And we want our machine to go on for thousands of seconds, or maybe days, or maybe months. Right? And so we want to be able to simulate all these different timescales. And we managed to be able to do this. The first thing is to average over the motion around the field lines. And that's that when we replace the particle by its ring of charge around the field line. That's called gyroscopes. The second thing to do is to average over the turbulent timescale. So what we do here is we solve one of those codes inside a flux tube inside the configuration. And we calculate what the turbulent fluxes are from this. And that takes about, it's equivalent to about 0.1 milliseconds of plasma evolution time. So on that timescale, nothing's really changing in the plasma as a whole, but the fluctuations are going ahead. We then take that timescale and we use that to evolve the temperature and the density of the plasma forward in time. And this multi-scale method has now come to fruition, really due to this fellow Bill Norland, who was a great colleague of mine, unfortunately died this last year. He developed these tools for his students. I was involved in some sense. But here's a very interesting thing. In this case, what they did is they tweaked the magnetic field, in this case in what's called a star ridge, or a three-dimensional device, and they reduced the heat flux by a factor of 2. So what I'm trying to make kind of that direction, right? So I'm going to give you a pitch, and it's the last thing I'll do, right? What we're doing now is we're trying to look for optimum configurations. How do we tweak that magnetic bottle to reduce the turbulence and make us get us close to fusion? And we can do this in the computer. We couldn't 5 years ago, but we can now. If we can combine this with AI tools, which we're already using to speed up these computations, right, we may be able to survey the sort of space of configurations and look for the optimum fusion configuration at that time. That will get us to fusion without guessing. I think fusion is needed. I think it will be foolish to try and do it faster than it's possible to do, because it will slow us down. But I think fusion is needed. I don't think we have all the answers at this time, and pretending we do will slow us down. Guessing is not a productive strategy. We've had 70, 80 years of fusion research. You're not going to guess your way to the answer. You need to have to be able to do so. And I think we have the tools now to be able to do that. Artificial intelligence may help us a lot. We find that we can replace a lot of the steps in codes now with steps in artificial intelligence that shortens the time to calculate configuration. It will allow us to survey all different configurations and come up with an optimum after that. So that's my pitch. Thank you very much for your time.
Thank you very much, Steve. That was a very lucid talk and very both inspiring and cautionary, and we conveying, I think, a lot of the excitement of the business right now, particularly over the last 5 or 10 years, and the promise for the future. Perhaps I could ask the first question, which is, you didn't have time to discuss inertial fusion, like as people are working on the Lawrence Livermore laboratory. Which do you think is going to come first, inertial fusion through inertial fusion or magnetic fusion? Granted that both will happen one day.
I'm supposed to give you the answer, it's very good fusion. But actually, they are that close that we can tell. And I think there's some obvious advantages to inertial fusion, but inertial fusion inevitably is a driven system. One of the nice things about an inertial system, especially Starlink, to be honest, is that it can be a totally standalone system that you don't have to take energy to make it make it, right? And obviously, there's a lot of developments in lasers and whatever you're driving your inertial system with. I think the results from this are spectacular, but I think the lesson from it is even more spectacular. That is, if you do this science, right, what looks like you're going down the wrong path, right, it can be reversed and checked. I think Bob and I were on a committee 15 years ago in the National Academy looking at the early results from NIF, and honestly, it was disappointing as hell, right? And they put it round by measuring very carefully what was going wrong and what they needed to do to make it go right. And this is the power of research, right? And you don't get that by cutting budgets, as it turns out.
A lesson from many other projects. Let me ask for other questions from the audience. Steve.
So, at least I need to hear you saying we're spherical.
So, well, the hole down the middle is very small. It's basically a donut that doesn't have the classic shape. It's got a very, very small hole down the middle.
Why is that good?
Well, it turns out that so more of the volume is on the inside of the fat particles on fundamentally. And so all of that volume has almost no turbulence. And there's only a bit of turbulence on the outside. And that seems to be the predominant effect. The other reason, and I'm not sure that this scales to a reactor, is to spin it very hard. It turns out in our experiment, it spins at almost supersonic speed in the middle of it. It's actually spinning at almost supersonic speed. And in the spherical Tokamak, that cones out the turbulence. It just stretches out all the turbulent eddies so much that they break apart before they actually do a lot of damage. But that doesn't scale to a reactor. I don't think we want a reactor this thing. It'd be hard to be able to inject the momentum inside to keep it spinning against the viscosity.
What will happen to the nuclear waste when this becomes commercial?
What will happen to
What will happen to nuclear waste? How will we
Nuclear waste.
nuclear waste? Well,
waste generated
so I could give you a whole talk about the nuclear part of fusion. Fusion is a nuclear technology. We have a neutron coming out of it, and it will activate the wall. And especially if you don't make the wall with the right materials, you could get a very highly activated wall. You've got tritium, you've got all those other things. So there is a smaller waste stream from a fusion part. But one of the most important things is you can choose that waste stream to be short-lived radioisotopes. So they have short half-lives, and hopefully, you can put it somewhere safe for a couple of 100 years. I could have showed you a graph of we use what's called low activation steels. These are steels without nickel. And what happens on those steels is that after 200 years, they have roughly the radioactivity of a lump of coal. And so you can reuse after a couple of 100 years, right? So that's to be contrasted with, the high level waste in coming from a fission reactor, which you have to store for an awful lot longer. I was very taken when I took over running lab in Britain. On my advisory council was a woman called Sue Ian, who was a nuclear engineer, and she said to me, and looked me straight in the eye, and she said, "We say fission until fusion is ready. Right, I'll continue saying that, you don't exaggerate the time scales. Maybe I did that myself.
Thanks for a great talk. So obviously there are a lot of challenges to getting a working electricity, like generating power plant. Which do you think is the biggest challenge that needs to be solved that you haven't mentioned in this talk yet?
Well, I think one of the ones that could actually stop the whole thing dead in its track is having materials to make the walls that are survivable with a in that flux of 14 MeV neutrons that come through them. It turns out that one megawatt a meter squared of neutrons on the wall produces 10 displacements of every atom in the wall in a year, full pattern, right? So you got your reactor going, the neutrons are going through the wall like this, and every atom in the wall moves 10 times in a year, right? From its equilibrium place. Now most of the time it drops back to where it was, right? Or something pretty steady. But sometimes it doesn't. What happens then is the wall loses structural integrity and falls apart. Now we're talking, and especially in high power density ones like these high magnetic field ideas that MIT is pushing, we're talking 6 or 7 megawatts per square meter of the wall, right? So that's 60 or 70, right, displacements per atom per year in the wall. Nobody efficient would take a material really above 100, right, and even 100 very, very rare. So there's a real question about survivability of the wall structure. Now the difficulty with that is that we don't have a fusion reactor to test the materials. They are building in Grenada. I was just outside actually. Grenada, a big neutron source. They have a deuterium beam that slams into a lithium sheet, and they make neutrons with a wide spectrum to test the fusion materials. It's going to come online maybe 2030, 2031, but it'll take 2 years to cook the materials and determine whether those little cubes of materials, they can radiate the bottom about that big, cook those materials and determine will they stay strong in the fusion neutron. So that's a real question, right? If that doesn't work, then the deuterium-tritium reaction is a no-go. And so it could be a showstopper. We had a community plan in fusion that we did in 2018, 2019. And we said that the one thing that we really need to do is to produce one of these accelerators to test the chip. And the one thing we haven't done is move that forward in this country. But the Europeans have. That's the place to go to for London, actually. Go to the Alhambra and one of the great sites in the world.
There's a free reverse configuration for the magnetic containment. Can you say turbulence problem?
A much worse field reverse configuration. The only way you can get field reverse configuration to really ignite is you have to drive it really, really hard. I'm very worried about the number of private fusion companies that are looking at field reverse configuration. Field reverse configuration is just basically a ring of current in your plasma like that. It has no external field. The currents in the plasma makes all of the current. Now, a ring of current will want to expand, right? Because opposite currents repel, so the left repels the right. So it wants to expand. And so to hold it together, you put it in the magnetic field. The magnetic field provides the Hooke force that holds it together. But if you think about that and you tilt that ring of current, immediately that Hooke force is now increasing the tilt. It's always unstable, trying to turn itself over the field. And so Trialpha Energy in Irvine, California, Helion Energy in Seattle, these are all companies liking the field reverse configuration because it's nice and simple, right? But it's bloody unstable. Right? I just don't know how in fusion conditions you'll ever hold it together. It will hold together when the orbit sizes are about the size of the machine, but you can't do that in fusion machines. I mean, it has to be big enough to contain, right? And so when you make a small field reverse configuration, you can find it stable, but if you just make it a bit bigger, it's not stable.
What, in the mice you're building up at Princeton, what gives it such a hypothetically high H factor?
This, we were talking about that, here, which is the volume in where the trap particles are, is much smaller compared to the volume where, there's no trap particles. Called the good curvature region, inside. It's very shifted over, so you've got this big region, let's say, and possibly this rotation. But what we're finding is when you, is very technical, when you take it up to high pressure, the codes are suggesting that when you take it up to high pressure, if you don't rotate it, then the turns get frequency.
Oh, beautiful. Last question.
Well, yes, Phil, we all have high hopes for detail, for reasons you know. What would you say is the future if it fails?
Well, I realize it might sound that I'm not enthusiastic about it, I'm incredibly enthusiastic. It will be the first time that we really burn fast. Okay. So the fact that I don't think that our route will take as necessary to commercial fusion doesn't mean I don't support doing it for very, very, very important. And we're almost there, so that's good. I think it even failed, right? And then people would take a step back from fusion probably for decades. And perhaps we would focus on inertial fusion at that point and look at that solution. I do think we should take seriously the sort of national program to really calculate the hell out of it. We can do it, and we're going to do it 5 years, right? That's what I'm trying to convince the Department of Energy.
Yes. There I would raise the spectre of timing in this context. But yeah.
I do all the time.
Yes. Look, I think that we're getting a little bit late, but I really thank Steve very much indeed for a wonderful talk that has taught a lot and been very honest about the opportunities, the excitement, the hard work that's gone into fusion. And if you want to learn more about this, and in fact in a slightly larger context, he's giving a second talk tomorrow at 3:30 in the same room entitled Stability, When Do Particles Explode? So that'll be here tomorrow at 3:30. So
Sorry, it'll actually be in 200, so.
oh, it's 200, sorry.
Tomorrow.
Okay, okay,
Yes.
okay, all right, good.
Thank you.
Okay, so
Sorry.
200. Oh, you all right? Oh, yeah, next door. Okay, well, thank you. Let's give. No.